Hey everyone, welcome to another episode of our Teach to Learn series. Today, we'll journey into the realm of algorithms and problem solving, exploring the intriguing technique known as backtracking. To illustrate its power, we'll tackle a classic puzzle, the n-queens problem. Get ready for an enlightening adventure into the world of computation. Backtracking in the world of algorithms is similar to a traveler navigating a labyrinthine maze. Picture yourself in this maze, where each turn presents multiple paths. As you explore, you encounter dead ends. What do? You backtrack, retracing your steps until you find a viable way forward. This process of exploring and backtracking forms the backbone of the backtracking algorithm, a versatile technique that empowers us to solve complex problems by systematically trying different paths and identifying the optimal route. Now, let's immerse ourselves in a practical application of backtracking, the n-queens problem. This puzzle poses a captivating challenge: how to position n queens on an n by n chessboard so that no two queens threaten each other. In other words, no queen can share the same row, column, or diagonal with another. Though it appears straightforward for smaller values of n, the complexity escalates exponentially with each increase. Imagine placing a queen on the chessboard. We must ensure this placement adheres to the fundamental rule: no two queens should attack each other. This means we must consider the row, column, and the diagonals each queen affects. Backtracking comes into play as we meticulously test different queen placements, evaluating their feasibility with the larger puzzle. If a placement leads to a conflict, we backtrack, undoing our steps and forging ahead on an alternate path. This iterative process continues until a valid solution emerges. Let us discuss on how backtracking works for solving the n-queens problem with n is equals to 4. In this problem, we aim to place n queens on an n by n chessboard such that no two queens threaten each other. Let's begin. We start with an empty chessboard. Let's place our first queen q1 in the first column of the first row. With q1 safely placed, and since no other queen may be placed in a column that already has a queen, we move to the next column for our second queen, q2. Unfortunately, first row is not safe for q2, as it is threatened by q1 in the same row. Let's continue searching for a safe spot. Still not safe, as it is threatened by q1 diagonally. Let's proceed to the next row. We found a safe spot for q2. Let's continue to the next column for q3, exploring the third column for q3. That is the column 2 here. Let's check the first row, row 0. The first row is not safe, as it is threatened by q1 in the same row. Let's check the second row, that is row 1. Row 1 is still not safe, as it is threatened by q2 diagonally. Let's try the next row, row 2. Row 2 is still not safe, as it is threatened by q2 in the same row. And finally, let's try the last row. The last row is still not safe, as it is threatened by q2 diagonally. It seems we've hit a dead end for q3 in third column. Let's backtrack and explore other possibilities. We find that we cannot place the current queen, q3, in any row of the third column. We now have to backtrack and alter the position of the queen whose position was decided before q3, that is, the queen q2. Next, we move forward again to find a safe position for q2. With q2 successfully placed, let's move on to q3. The first row is not safe for q3, as it is threatened by Q1 in the same row. Let's try the next row. We've found a safe spot for Q3. Let's continue to the next column. With Q3 successfully placed, let's move on to Q4. We know the first row is not safe for Q4 as it is threatened by Q1 in the same row. Moving into the second row, still not safe as it is threatened by Q3 in the same row. Now moving into the third row, still not safe as it is threatened by Q3 diagonally. Finally, moving to the last row, it is not safe as it is threatened by Q2 in the same row. It appears we've reached a dead end for Q4 as well. Let's backtrack again. As we cannot place the current queen Q4 in any row of the fourth column, we have to backtrack and alter the position of the queen, whose position was decided before Q4, that is Q3. Third row for the third column is not safe as it is threatened by Q2 diagonally. And finally, the last row for third column is not safe as it is threatened by Q2 in the same row. Looks like we've reached the dead end again. Let's backtrack. We found that we cannot place Q3 in any row of the third column, so we have to backtrack and alter the position of the queen, Q2, whose position was decided before Q3. As Q2 is already in the last row of the second column, we will need to backtrack one more time and alter the position of the queen Q1, whose position was decided before Q2. Let's place Q1 in the second row of the first column. With Q1 safely placed, we move to the next column for our second queen, Q2. First row for the second column is not safe as it is threatened by Q1 diagonally. Still not safe as it is threatened by Q1 on the same row. Third row, second column is still not safe for Q2 as it is threatened by Q1 diagonally. Finally, we've found a safe spot for Q2. Let's continue to the next column. We've found a safe spot for Q3. Now let's continue to the next column for Q4. First row for the third column is not safe as it is threatened by Q3 in the same row. Similarly, second row for the fourth column is still not safe as it is threatened by Q1 on the same row. Finally, we've found a safe spot for Q4. Finally, we've found a solution of placing 4 queens on the board such that no 2 queens threaten each other. And that concludes our walkthrough of backtracking on the n queens problem with n is equals to 4. In the next episode, we'll dive into the code implementation of the n queens problem using backtracking. We'll walk through the steps of writing the algorithm and explore how we can use backtracking to find a solution where no 2 queens attack each other. Get ready to see the code in action and gain a deeper understanding of how this algorithm works. Additionally, we'll investigate the intriguing question of just how many ways n queens can be placed on the board, while adhering to the rule of non-attack. As we wrap up this video, remember that the coding is full of endless possibilities. So, until our next episode, keep coding, stay curious, and keep exploring new horizons. Whether you're tackling challenging algorithms or building innovative projects, the journey of learning never stops. Every line of code you write takes you one step closer to becoming a coding maestro. Be sure to check out our upcoming episode where we'll dive deeper into the code and explore the world of n-queens problem solving with backtracking. Until then, keep those creative gears turning and may your coding adventures be as exciting as the solutions you seek. Thanks for joining us today, and don't forget to like, subscribe, and hit that notification bell so that You won't miss any of our coding explorations. Until next time, keep coding, keep learning, and keep pushing those boundaries.